Hello Year 10, this video is a summary video on the topic energy changes. First of all, in this topic we discuss the conservation of energy, which says that during a chemical reaction energy is conserved. This means that there is the same amount of energy before and after reaction. This means that energy is just transferred, not created or destroyed. Then we went ahead and looked at some types of reactions. The first of which we looked at was exothermic reactions. And this is a reaction where energy is transferred from the reaction to the surroundings. This means that the products have less energy than the reactants because some of that initial energy has been transferred to the surroundings. This is why when we feel the reaction it feels hot, because some of the energy has been transferred to us as part of the surroundings. Some examples of this include combustion, oxidation and neutralisation reactions. We are able to show the changes in energy of a reaction using a reaction profile diagram. This one is an example of an exothermic reaction. As you can see, the products have less energy than the reactants. We can tell this because they are drawn at a lower level. This means that energy has been given out, and that is shown by the green arrow. We also have this blue arrow which tells us how big the activation energy is, which is used to break bonds, and we'll come back to this a little later. The second type of reaction that we looked at were endothermic reactions. These are reactions where energy is absorbed from the surroundings. So energy is taken from around the reaction and absorbed into it. This means that the products have more energy than the reactants, and these are the ones that we would feel cold if we touched them because it's transferring energy from us to the reaction. An example that we looked at was thermal decomposition. And again, here is the reaction profile diagram for one of these reactions. As you can see, the reactants are lower in energy than the products, and this time we have a positive energy change. The green arrow is pointing up. But still, we have this blue activation energy, which we will discuss now. So, the activation energy. Reactions only occur when the reacting particles collide with enough energy to react, and it is this energy called the activation energy, which is the minimum amount of energy needed to react. So if particles collide with less than this energy, they will not react. This energy is needed to break the bonds in the reactants so that atoms can rearrange and make the products. And this energy is what was shown in those blue arrows on those reaction profile diagrams. You may remember that we did an experiment as part of this topic. It is one of your required practicals, and we investigated the change in temperature. We can use the apparatus shown to investigate a change in the temperature during a chemical reaction. First of all, we recorded the initial temperature of the reaction mixture, and then we recorded the maximum and minimum temperature that was reached during the reaction. Our example was we added an acid and an alkali. First we measured the temperature of one of the reagents to get the starting temperature, and then we kept checking the temperature as we added the other reactant and watched the reaction progress. We saw an increase in temperature because it was an exothermic reaction. We could also consider how the changes in reactant quantities or concentration might affect this temperature change. So in our example we changed the amount of one of the reactants to see how that affected the overall temperature change. This is a really common part of the exam paper. They like to take the required practicals that we do in schools and ask you questions about them. So next we're just going to go through an example of this. So here we have an example question that might be asked about a required practical. These questions can be presented in many different ways. Some you have to suggest improvements to a given method, others you have to suggest an entire method by yourself, and some you have to use the data given to you and discuss both accuracy and precision. Pause the video on each part of the question and have a go. You will need a calculator for one part of the question, so you may wish to pause this video and go and get a calculator now. Just read through the beginning of this question, pausing as needed, and then when you're ready, restart the video and we'll move on to the first part of the question. So, this is the first part of the question. As you can see, I've just screenshot a part of the original bit that we just read to remind you how much of acid we were measuring out. So, pause the video and decide where you would draw the lines. Okay, so if we're drawing one line from each measurement to the most suitable piece of equipment we would use to make the measurement. So, to measure the temperature of the solution, we would use a thermometer. We've done this many times in class before. To measure the volume of the hydrochloric acid, we could use a beaker or a measuring cylinder. Both of these pieces of equipment help us to measure volume. But as you can see by the little clip out at the top, we only need to measure 25 centimetres cubed of hydrochloric acid. So using a measuring cylinder would be much more accurate, and that would be the appropriate piece of equipment to use. Okay, here's the next part of the question. Pause the video here and have a go. First we have to decide which result is anomalous, so it doesn't fit the pattern. Looking at this data, we can see that experiment 2, where the temperature rose by 7.8 degrees, is the anomalous piece of data. All of the others were in the low 6 degrees. This means that our calculation would be 6.1 plus 6.1 plus 6.4 equals 18.6. We then divide this by the number of experiments used in the average, which is 3. So 18.6 divided by 3 should get you an average maximum temperature rise of 6.2 degrees Celsius. If you're unsure on how to do this, go back to our work on chemical calculations and look at the equation for calculating a mean. Next, this is the final part of the question, so pause the video and have a go. Great. Remember, accuracy is how close something is to the true value. Picture the centre of our dartboard that we drew in class. Remember, precision is how close the results are together, and we represented this by having lots of points near together, but not necessarily near to the bullseye of the dartboard. So, which of these suggestions would help us get a true value? For a true value, we need to measure all of the temperature rise, so we must limit any energy loss to the surroundings. For this, the best answer would be to put a lid on the polystyrene cup. Polystyrene is an insulator and will help prevent any energy being lost to the surroundings. Using a metal beaker would actually make the experiment less accurate, because metal is a really good conductor of heat, which would mean we would lose more thermal energy to the surroundings. Using a thermometer with a resolution of 1 degree may improve the precision of our measurements, but it would not improve the accuracy. Okay. This next part of the video now is for higher tier, so if you feel like you are not going to be sitting the higher tier paper, thank you very much. You can now close the video. You have completed this part of this week's task. If you are doing the higher tier video, I really recommend you carry on listening for another few minutes, and we will discuss making and breaking bonds. So, as you can see on the slide, energy is needed to break the bonds in the reactants. This part of the reaction is endothermic because energy is absorbed from the surroundings. But when the bonds in the products are made, energy is given out, which is exothermic. So we can compare the energy absorbed when breaking the bonds and the energy released when making the bonds to calculate the overall energy change. So if more energy is absorbed when breaking the bonds, the overall reaction is endothermic. Whereas if more energy is released when making the bonds, energy on overall is given out to the surroundings, meaning we have an exothermic reaction. The energy needed to break a bond is called the bond energy. The same amount of energy is needed to break a bond as is needed to make a bond. Okay, so when attempting any bond energy calculations, these are the steps that we need to take. We need to balance the symbol equation to make sure that we can see all of the bonds in the whole reaction. There's then an optional step which some people find really useful, which is to draw out the molecules, and I personally always draw out my molecules so that I can physically count how many bonds are present. We then calculate the energy required to break all of the bonds, and then calculate the energy released by making all of the product bonds. We can then use this to calculate the overall energy change. So the overall energy change is calculated by calculating the energy absorbed from the surroundings and then minusing the energy released to the surroundings. If the answer is negative, more energy was released than absorbed, so the reaction is exothermic. If the answer is positive, more energy was absorbed than released, so the reaction is endothermic. You can check your answer by seeing which of the two energy calculations was highest, the energy needed to break or the energy needed to make the bonds. Okay, we're just going to go through an example to try and explain this a little clearer. Okay, so we're going to use the equation below and the bond energies to calculate the energy change for the production of ammonia from hydrogen and nitrogen. Then we need to state whether the reaction is exothermic or endothermic. So pause the video and try this example. If you need some additional help, I will be going through the answer step by step, so you can pause at any point once you feel more comfortable. Okay, so step 1 was to balance the equation. As you can see here, we've had to put a 3 in front of the hydrogen and a 2 in front of the ammonia to ensure that our equation is balanced. I haven't done this on the screen, but I would really recommend that you all draw out these molecules to help you count the bonds in the next part of the question. So pause here if you now feel comfortable at calculating the energy required to break the reactant bonds now we've balanced the equation. If not, let's move forward. Okay, so to calculate the energy required, we have this number here, which is 3 times 436. So that comes from the 3 hydrogen molecules. If you look down in the table below, you can see that the bond hydrogen to hydrogen has a bond energy of 436, and we have 3 of them in our balance symbol equation. We've then added 945 kilojoules a mole, and that's the bond energy associated with a nitrogen bond. So nitrogens are triple bonds and are very, very strong, and we can see that in this table here. So once you've done this calculation, you should have 2,253 kilojoules per mole. So the next step will be calculating the energy required to make the product bonds. If you feel comfortable, go ahead and do this yourself with the video paused. If not, let's follow along with me. Okay, step 3. So we needed to calculate the energy required to make the product bonds. So in our product, we have 2 molecules of ammonia. In each of these molecules, we have 3 nitrogen to hydrogen bonds. So in total, we're going to have 6 nitrogen to hydrogen bonds. So you can see here in the calculation, I've done there's 2 molecules, and in each molecule, there is 3 nitrogen to hydrogen bonds. And you can see where I've got that number from in the table below. And that equals 2,346 kilojoules per mole. So the final step of this bond energy calculation is to calculate the overall energy change now that we have the energy required to break the reactant bonds and the energy required to make the product bonds. So here is the final part of the calculation. So as you can see, we have done our calculation and got a negative number. So because the energy change is negative, the reaction is exothermic. And I hope this now makes a bit more sense to you all. and we will see you all soon. Take care.